All right, we're going to head into our last unit for the year, and we're going to talk about two different types of functions that are related to one another, and they bring in a couple of new operations that we didn't think existed before. So they are called exponential functions and logarithms. But before we get into logarithms, we got to know more about exponential functions. So I'm going to ask you some questions on these two funny-looking equations. Okay, and the questions are all going to be about sketching the graph, and we're going to see if the function is an exponential growth or an exponential decay model, and then we're going to explain our answer as to why. So let's first go into where we've been so far and what we've been through before we get into the next thing. So all the functions we've dealt with so far have been linear. If we had y equals mx, plus b, and that was a linear function. We've had quadratics. We've had higher order functions that we've dealt with. We have had absolute value functions. We've had, by the way, what shapes did they made? Something like this. We've had cubics and higher orders. We've had absolute value. Our latest thing has been, square roots, and so and their inverses. So we have seen all sorts of stuff based off of operations, and the operations that are recurring. But what we've never seen before? We've never seen an equation, a function that had a y and an x. What we've never seen before? An x as an exponent, right? We've seen exponents before. But what if the x was the exponent? What if we had something that looked like this? Where we have our y equals, but we have our x and the exponents. And so since the input, the independent variable, is in the exponent, we call this an exponential function. And that raises an entirely new operation. Okay, so remember how when we were talking about square roots and how they roots had undone exponents. Well, what if the variable is actually in the exponent? It's called an exponential function. And so the whole the fact that this even exists brings up an entirely new set of things that we can deal with. And so we're just going to jump right in to figure out, well, let's play around with that and see what can happen. And so I give you a couple of problems, and we're going to see what might be occurring here. And then we'll go more into detail in the next lesson. But for right now, two basic equations, and we're going to sketch the graphs, label them as growth or decay, and then explain the answer. All right. So if you look at the equation in problem number 1, we see, again, this is something that's a little bit new. We've seen a whole bunch of stuff before, but we've never seen our x in the exponent. And so remember, there were 3 keys to handle anything that we've never seen before. The first key is to make an xy table. We can handle anything if we had an xy table. Okay, so that's the first key to success. The second key to success is, if we're going to make an xy table, what if x was 0? All right, so that's going to be the second key to success. So we're going to play around with, what if x was 0, and see what we get for y. So let's start with that and plug some stuff in. So we have y equals 2 times 1/4 to the 0 power. And now we have to remember a few things from the last unit. We have to remember some laws of exponents. And this substitution of x equaling 0 brings in a law. Okay, so law. Anything to the 0 power is equal to 1. And we have to remember that law. So 1/4 to the 0 power is actually 1. So we'd be looking at y equals 2 times 1, which of course is 2. So if x is 0, y is 2. And now we'll play around with some things before we jump into the third key, because this is the second key to graphing right here. The second key to graphing is what if x was 0. So we're going to play around with some more things. So we know what would happen if x was 0. Well, what if x was 1? So let's play around with that. Okay, so we'll try, what's going to happen if x is equal to 1, and we'll do some work down here. And then we have 1/4 to the first power. Okay, so we know some basics. 1/4 to the first power is just 1/4. And 2 times 1/4, of course, is 1/2. So if x was 1, y equals 1/2. Let's see what would happen maybe when x equals 2. What would occur there? So let's play around with x equals 2, and we'll have maybe a pretty decent idea of what's happening halfway through. So if x is equal to 2, we would have y equals 2 times 1/4 to the second power. And this is where we have to start being careful with some basic, elementary level fraction work. 1/4 to the second power, remember, is 1/4 times 1/4. And that, of course, is 1/16. Okay, so we're looking at y equaling 2 times 1/16, which is 1/8. All right, so let's take a look at what's happening here. So we have to pause and see if we can see a pattern. So as x is getting bigger from 0, what's happening to y? Okay, as x is getting bigger, y looks like it's getting smaller. Okay, so as x is getting bigger, y is getting smaller. We have to pay attention to some things. All right, and this is, that's what life is all about, paying attention to things. So we can see what's happening. X is getting bigger, y is getting smaller. How small will y get? Okay, so this is some of the things we have to think. How small will y get? And we have to wonder, remember this, the third key to graphing, can y ever equal 0? All right, so this is the third key to graphing. Is there any possible number that we can substitute for x where we have y equaling 0? Okay, so let's take a look. Maybe some crazy stuff is going to happen. So would y ever be 0? Would this equation ever have a solution where we could solve for x? And you may be wondering, how in the world can we even solve for x? And we'll actually get into that later in the unit. But for right now, before you start going into mechanics, I want you to think. Put your thinking cap on. What possible number can we substitute for x that would make this 0? All right, because we know this law, anything to the 0 power is 1. So even if x was 0, this would be 1. But what about this other law? This other law at play. What if x was negative? Do you remember the other law that dealt with negative exponents? Law. Anything to the negative power is 1 over that thing to the positive power. Does it change the fact that this is a positive thing? No. So we have to think. And the more we're thinking, we start playing around with some options. There is no way that we could plug in anything for x and it would be 0, because if we plug in a positive number for x, we know it's getting smaller and smaller and smaller. And if we plug in a negative number for x, it's not going to be negative. It's going to remain positive. So could y be 0 at all? And then you realize, no, it's impossible. Y can't be 0. And so maybe we're thinking, well, if x keeps getting bigger and y keeps getting smaller, how small can y get? Well, let's play the what if. What if x was 1,000? Holy cow. So what if x was 1,000? We would have this, y equals 2 times 1/4 to the 1,000th power. And is that going to be a negative number? No. I mean, remember how exponents work. We're multiplying 1/4 times itself 1,000 times. And so basically, we would have 2 times 1 over 4 to the 1,000th power, which is a pretty large number. I don't feel like going there. So that's just a very, very, very small positive number. Okay, it's still not 0. It's just a very small positive number, and that's important to distinguish. So y won't ever be 0. We've established that, and we know that x is getting bigger, y is getting smaller. So what happens if x is negative, right? So let's play around with that. Could we have a possibility where x is -1? All right, so if we substitute for x is -1, now I'll start using this side because I'm like writing a whole bunch of stuff here. If we substitute x is -1, what do you think will happen? I want you to remember your laws of exponents. Remember this law of exponents. Anything to the negative power is 1 over that thing, right? So believe this. Think now, before I reveal it. I don't want to steal thinking from you. What is going to happen here with 1/4 to the -1? Thinking about our laws of exponents. So I've given you a chance to think. If you haven't put your mind to it right now, I am stealing thinking from you. Don't let me steal thinking from you. 1/4 to the -1 power is actually +4. Okay, so using that law of exponents, 1/4 to the -1 power is actually +4 because it's 1 over 1/4. 1 over 1/4 is 4. So if x is -1, y is equal to 8. Isn't that amazing? X is -1, y is equal to 8. And what if x was -2? All right, so let's see this. Again, we have to know these laws of exponents. What if x was -2? So what would that mean? That would mean we're dealing with 2 times 1 over 1/4 to the +2 power. And you can do some, hopefully you're seeing a shortcut by now. If you're not seeing a shortcut, you really aren't thinking, and I want you to think. If you don't see what's happening now, you're not thinking. I want you to think. So we'd have 1 over 1/16. And what's 1 divided by 1/16? Please put your thinking cap on. Don't let me steal from you. It's +16. So if x was -2, y is 2 times 16, or 32. Okay, so we see what is happening here with this table of values. All right, so we have this crazy-looking equation where the x is in the exponent, and we make our table of values, and we've used some laws of exponents that we learned from the last unit and some basic math, and hopefully you're thinking. I want you to see some shortcuts here that you can be able to do this quicker. You can see what's happening with that table. And so now that we have the table, let's sketch the graph. Okay, so what might be happening here? We can look at our table of values and see, well, what are the x values that we're going to be dealing with, and what are the y values that we're going to be dealing with, and maybe we'll see what's happening. So our first order pair that we came up with was 0, 2. We knew that. 0, 2. Our second order pair is 1, 1/2. So our x is 1, y is 1/2. Our third order pair is 2, 2 and 1/8. So when x is 2, y is 1/8. It's even less than 1/2. It's not 0, it's just less than 1/2. So you can see what's happening here. It looks like a little bit of this action so far. And we've established that no matter what, y is going to equal, or it can't equal 0. So it's not going to really touch. It's going to look like it's touching, but it really is not. And we also know that if x was 1,000, we would have y being some very, very small positive number. So basically, if x is 1,000, y is some very, very small positive number. It's going to continue moving in that direction like so. All right, so hopefully you can see that's what's happening as x is getting bigger. Y is getting smaller, just never touch 0. So what about on the other side of 0? What's going to occur when x is -1? Well, when x is -1, we have +8. Well, that's interesting. So at -1, we have 1, 2, 3, 4, 5, 6, 7, 8 way up here. And if x is -2, y is at +32. I didn't catch that before. +32. All right, so the graph is going like this. And so you see it's just continuing, as the further we go to the left, the faster it's moving towards infinity, and the further we go towards the right, the slower it's going towards 0, but it'll never touch 0. So this is the graph of an exponential function. So the question then is, well, here's our equation. Y equals 2 times 1/4 to the x power. The question, is this exponential growth or is this exponential decay? And let's hold on to that question right now. We're going to come back to it because I don't understand how to read that yet, so let's come back to it. In the meantime, let's graph number 2. What would happen if we switched our y and or not the y and the x, if we switched the 2 and the 1/4? So what would occur? Okay, what would occur? And we're going to do the same thing, but hopefully this time I'll move quicker because now you know some laws. And since I've given you the opportunity to think, I'm not going to lose you when I do some things a little bit faster. Okay, so we have this. Don't know what it's going to look like. We make our xy table, and then we start figuring some stuff out. When x equals 0, we plug in 0 for x. 2 to the 0 power is 1. So when x is 0, we're looking at y equals 1/4 times 1 because of that law. Right? We've used the law of exponent. Anything to the 0 power is 1. So if x is 0, y is 1/4. And if we had x equaling 1, okay, so we have 2 to the first power. So we'd have y equals 1/4 times 2, which of course is 1/2. And if x equaled 2, 2 to the second power is 4. So y equals 1/4 times 4, which is 1. I'm not quite sure how that's going to look yet. So let me play one more. If x equals 3, y would equal 2 to the third power, which is 8. So 1/4 times 8, and that of course is 2. So you see, you have a pretty good idea of what's occurring here. Now again, we'll ask the same question. Can y ever be 0? Right? What possible number can we plug in for x that would make y 0? Because so far, as x is getting bigger, y is getting bigger. Right? So now we can see as x is getting bigger, y is getting bigger. So what would happen, what number would exist for that to be 0? If we plug in a bigger number for x, well, this would be a bigger number for y. So that ain't the case. What if we picked a smaller number for x? What would happen if x were negative? So let's skip that for a second. Let's go into what if x were negative 1? So we jump into that. Y would equal then 1/4. What's 2 to the negative 1 power? 2 to the negative 1 power is that law of exponents, 1/2. So if x was negative 1, y would be 1/8. Well, that's interesting. So that's getting smaller. What if x were negative 2? If x were negative 2, whoop, wrong color there in the graph. If x were negative 2, y would then be, all right, so 2 to the negative 2 power. Remember your laws of exponents. 2 to the negative 2 power is actually 1/4, and that would be 1/16. So if x is negative 2, y is negative 1/16. So it looks like as x is getting smaller, y is also getting smaller, but maybe it'll touch 0. So let's pretend. What if x was negative 1,000, right? Then we would have y equals 1/4 times 2 to the negative 1,000. Would that make it a negative number? Does it cross 0 ever? And then we got to think, well, that would be 1/2 to the 1,000th. And again, that's not going to give me a negative number. That's just going to be a super small positive number. So we'd have, if x was negative 1,000, we would have a super small positive number. Still not a negative number. So you can clearly see that there's no possible way our y could be 0. So again, in this case, there's no x that we can plug in that would give us a 0 for y. So we have our table of values set up. And hopefully you were thinking, hopefully you weren't just here to copy me. You have to put your thinking brains on. All right, so we're going to sketch our graph. We know some things about some things, so we'll put some numbers down, like 1, 2, 3, and then -1, -2, -3, and then like 1, 2, 3, 4, 5, and then we'll see what's going to happen. All right. So the first order pair we come up with is 0, 1/4. So 0, 1/4 is like, I don't know, around here. We'll say, I don't know, we'll estimate. Then we have 1, 1/2. So 1, 1/2, that's a little bit bigger than 1/4, right? It's halfway through. And then 2, 1. Okay, so 2, 1 is right here. And then 3, 2. Ooh, look what's happening. Look what's happening, right? As x is getting bigger, y is getting bigger. How big, how fast, right? Well, what if x was 4? If x was 4, right? 2 to the 4th power is 16 divided by 4 is 4. So if x was 4, y is 4. Look how fast that's growing. Look how fast that's growing. That's interesting. Whoa, did you hear what I just said? Hint, hint. Look how fast that's growing. All right, so let's go in our negative numbers. So we have -1, 1/8. -1, 1/8 is like down here. -2, 1/16 down here. And even at -1,000, it would still be a very, very small positive number. So it's not going to cross the y-axis, or the x-axis, excuse me. It's not going to cross the x-axis. So it'll keep going in that direction, and it's going to keep getting bigger, bigger, bigger. And there is our exponential function. Wow, this is crazy, right? I hope so, because it's fun. Oh, so much fun. So we have our graphs, right? We had the graph of the first function, which looked like this. And the graph of the second function looked like this. All right, so what's happening? Remember the other question that we were asking. Label the function as exponential growth or exponential decay. So clearly, with the second graph, the graph of number 2, remember we were saying the bigger x gets, the faster y grows. So clearly, graph number 2 is exponential growth. And you hear this. You hear this in the news. You hear this in the media. You hear this in worlds when especially when people are speaking in hyperbole. They'll say, that keeps growing exponentially. Like, I doubt that whatever you're talking about fits this model, but I understand what you're saying. My income is growing exponentially. You wish. More likely it's linear, but who knows? We'll figure that out later. But you hear this exponential growth happen all the time. So the graph of number 2 is clearly exponential growth. So what does that mean for the graph of number 1? So if this is happening with number 1, as x is getting bigger, y is getting smaller, 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 closer to the 0, this is exponential, the opposite of growth. Exponential shrinkage? Well, no, we give you that word. It's exponential decay. That's the word. Decay is, not growth. It's shrinkage, and you hear it in science with half-life and all that stuff for radioactive chemicals. So you have exponential decay. So the graph of number 1, exponential decay. The graph of number 2, exponential growth. Now, the last thing I said, explain your answer. Well, one explanation clearly is duh. Look at the graph. Okay, so you're thinking, duh, look at the graph. But it's not so much duh, look at the graph. It's look at the graph and the fact that, well, y will never be 0. Y is going to always be greater than 0. Since y is greater than 0, it's always going to be greater than 0, clearly it's going to be exponential growth. So it's not just the fact, duh, look at the graph. Look at the graph. Y is going to always be greater than 0, so it's clearly growing exponentially. It's clearly growing exponentially. And that's why we can say, duh, look at the graph. And then the explanation for the graph of number 1. Is this exponential growth or decay? Well, duh, look at the graph. Okay, so the graph is so cool. Since y is greater than 0, it's always going to be, positive y. It's decaying exponentially. It's not growing, it's decaying exponentially. So that's one explanation, okay? Last explanation, shortcut. So here's a shortcut. So we've done all the hard work. If you've gone this far, you've earned the shortcut. The exponential model can tell you. If you have an exponential model that fits this description, right? And if you have something that looks like this, and you know that this constant number out here, that constant number a, is a positive number, right? If a is a positive number, and it's being multiplied by something being raised to the x power, okay, and this other number, this exponential thing here, this being raised to a certain number, if this is greater than 1, if it's greater than 1, then guess what? If it's greater than 1, it's exponential growth. If it's less than 1, then we're dealing with decay. Okay, so this number here, if it's greater than 1, we're dealing with exponential growth. If it's less than 1, it's dealing with exponential decay. Let's put that to the test. So you remember in graph number 1, we had this being a positive number, this being less than 1. Hopefully you know 1/4 is less than 1. Guess what we had? Exponential decay. Boom! All right, so that seems to have worked. If you can memorize that, cool. And then look at graph number 2. Here's the positive a being a positive. I don't care that it's 1/4, it's still a positive number. And then there's b here, this number being greater than 1. Guess what's happening? Exponential growth. Look at the graph. Boop! Okay, so here's your exponential model. Y equals a times b to the x power. Now hopefully what you're thinking is this. Well, if b is greater than 1, it's growth, and if b is less than 1, it's decay. You might be thinking, well, what if b was 1? What if b was 1? And I'm going to end the video there, because I want you to think about that for a second. What if b was 1? Is it growth? Is it decay? You tell me. And if you haven't figured it out by now, well, shame on you. Because what if b was 1, here's how you can figure it out. Graph it and tell me, okay? Not tell me. Graph it and tell me, and you'll know the answer. All right? So get some practice done. You have the assignments and all that good stuff. But that's it on exponential models with growth and decay. And we'll learn more about graphing exponentials in the next unit. Thank you.